we have seen operational amplifier. In operational amplifier we have seen open loop configurations. So we have seen three types of configuration. The first one is inverting operational amplifier. Second one is non-inverting, and the third one is differential operational amplifier. Okay, so we have seen the open loop configuration in operational amplifier. First is inverting, second one is non-inverting, and the third one is differential amplifier. So the main disadvantage in case of open loop configuration is that in case of open loop, V output it is equal to VID into A. Okay, where A is the gain of the operational amplifier in open loop. Okay, and VID it is equal to differential input voltage. Okay, so VID it is the differential input voltage. So even for very small VID we are getting V output it is going to saturation. V output it achieves plus minus Vsat even for VID. If it is very small, then also we are getting saturation output voltage. Okay, this is the main disadvantage of open loop configuration. Okay, so for linear application open loop configuration is generally not used. Okay, so we have to think for closed loop operational amplifier. So what is this closed loop operational amplifier? Okay, suppose this is any amplifier circuit, operational amplifier, this is V out, and say this is VID, this is terminal 1 and terminal 2. Okay, suppose some portion of V output, if it is fed to the input, then this is known as feedback. Okay, so if we are using feedback, so some portion of the output if it is given to the input, then this is known as feedback. Okay, so there are two types of feedback. First one is positive feedback, and the second one is negative feedback. Okay, so in case of operational amplifier, in closed loop operational amplifier, then we will be using negative feedback. Okay, so what is the difference between positive feedback and negative feedback? In case of positive feedback, the feedback signal will be in phase of the input, and in case of negative feedback, the feedback signal, that is some portion of the output, it is fed back to the input, and the feedback signal and the input signal both will be in opposite phase. Okay, that is why it is known as negative feedback. And for positive feedback, the input signal and the feedback signal both are in same phase. Then we will study about closed loop operational amplifier. Again, in closed loop operational amplifier, we have to study about first is inverting amplifier, second one is non-inverting amplifier, and the third one is differential amplifier. Okay. So again, in closed loop operational amplifier configuration, we will have to study about inverting amplifier, non-inverting amplifier, and then the differential operational amplifier. These three configurations are in closed loop configuration. Closed loop configuration means here feedback will be used. Okay. So first of all, we will see about inverting amplifier. Okay, so circuit diagram of inverting operational amplifier in closed loop. This is in closed loop configuration. Okay, so first of all, we will see its diagram, circuit diagram. So this is the circuit diagram of inverting operational amplifier in closed loop configuration, and it is connected to plus VCC, and here it is minus VEE. Okay. Okay. So this is the circuit diagram of inverting operational amplifier in closed loop configuration. In inverting operational amplifier, what we are seeing is that here feedback signal is given to the inverting input, okay, and this Vin, that is the input voltage, is applied to the inverting terminal of the operational amplifier. Okay, so we have to see how we can express V output in this case. Okay, suppose this point is A and suppose this point is B. Okay, now we know that the input resistance of operational amplifier in ideal case it is infinite. So IA and IB, since Rin it is equal to infinite in ideal case. In ideal case, so we have IA it is equal to IB it is equal to 0. So no any input current will flow. That is IA it is equal to IB it is equal to 0. Okay. Now for ideal case, A is infinity, A it is infinite. Okay. So A it is equal to V output divided by VID. This is VID. VID it is equal to infinity. Okay, in ideal case. So we can write V output divided by VID is what? VID it is VB minus VA, it is equal to infinite. So for this VB minus VA, it will always be equal to 0. So if this term is 0, then this will be infinite. Okay, so VB, it is equal to VA. Now here VB is at ground potential. VB is connected to ground. So VB is equal to VA and it is equal to 0 volt. So VA, it is equal to ground 0. So it is virtual ground. So this is the concept of virtual ground. Okay, virtual ground. In virtual ground, see, point B, it is connected to ground and VB, it is equal to VA. Okay, so VA, if it is equal to 0, so point A, it may be considered as a virtual ground. Okay, so this is the concept of virtual ground. Now we will express V output. How we can express it? We can see. Now in this figure, see, IA, it is equal to 0. So current I1 and this is current IF. Current I1, it is flowing across R1. Current IF, it is flowing through RF. Okay. Now I1, and since IA, it is equal to 0. Just now we have seen IA and IB both are equal to 0 because Rin is very high. In either case, it is infinite. So IA, it is equal to 0. It is equal to 0. Okay. Now under this case, I1, it is equal to IF. Okay. So how we can express I1? It is equal to V in 1 minus VA divided by R1. It is equal to VA minus V out divided by RF. Suppose this is equation A. Okay, so we can write this equation here. It is V in 1 minus VA. So what is VA? VA, it is equal to VB, it is equal to 0 volt. So we can write minus 0 divided by R1, it is equal to minus V naught divided by RF. So from this, what we are getting? From this, what we are getting? V in 1 by R1, it is equal to minus V naught by RF. So V naught by V in 1, it is equal to minus RF by R1. Okay, what is this V? V output divided by V in 1? AF, it is equal to V out divided by V in 1. So this is AF. What is AF? It is closed loop gain. Inverting operational amplifier closed loop gain. AF, it is closed loop gain. Closed loop gain of inverting operational amplifier. Okay, AF, it is equal to V out divided by V in 1. Okay, so we can write AF, it is equal to minus RF by R1. Okay, so we can express V output. V output, it is equal to minus RF by R1 into V in 1. AF, it is equal to minus RF by R1. This is closed loop operational amplifier gain, inverting operational amplifier gain in closed loop connection, and V output we can express it is equal to minus RF by R1 into V in 1. Okay, so this is equal to AF into V in 1. Okay, now if RF is equal to R1, if RF is equal to R1, then in that case V output it is always equal to minus V in. So this inverting operational amplifier, it can be used as sign changer circuit, okay, or phase changer circuit. Okay, this is V in 1. Then V output it will be amplified. It will be amplified from this. It will V output we are getting like this, minus RF by R1 into V in 1. So it will be, its phase will be 180 degree with respect to V in. Okay, so it will be amplified based on RF and R1. So we can vary V output, or we can vary AF by varying value RF and by varying value R1. Okay, because here we are saying that this is ratio minus RF by R1 into V in 1. Okay, so we can vary V output by varying R1 and RF. Okay, and if RF is equal to R1, then in that case it is equal to V output, it is equal to minus V in 1. So it is a phase changer circuit or sign changer circuit. Okay, now we can see that here V output it is equal to minus RF by R1 into V in 1. Okay, so it can be considered as a voltage controlled voltage source. It is controlled by RF, R1 and V in 1 output. Okay, so it is also known as a voltage controlled voltage source. So this is all about inverting operational amplifier in closed loop configuration. Then we will see about second one, non-inverting operational amplifier in closed loop. So first of all we will see the circuit diagram. So this is the circuit diagram of non-inverting operational amplifier in closed loop configuration. Okay, so in this circuit we are giving the input signal to the non-inverting terminal. This is non-inverting terminal and this is inverting terminal. Okay, so again here we will apply virtual ground concept. Virtual ground concept in order to determine V out. So we have to determine V out for this non-inverting operational amplifier in closed loop configuration. Okay. Now you can see IB is equal to 0, IA it is equal to 0. Just like previous one, the current IA it is equal to IB it is equal to 0, because in ideal case Rin it is equal to infinite in ideal case. So IA it is equal to IB it is equal to 0. So this is equal to 0. IA and IB both are equal to 0. And second case, here A is infinity. This A is infinity in ideal case. Again in ideal case. So how we can express A? A is V output divided by VID. It is equal to infinite. Okay. So VID it should be equal to 0, because here it is infinity. So if VID it is equal to 0, then only this term it will be infinite. Okay. So what is this VID? VID is VB minus VA, it is equal to 0. This is VID. This is VID. That is the differential input voltage. VID is the differential input voltage. It is VB minus VA. VB is to the non-inverting terminal and VA it is connected to inverting terminal. Okay. So from this we can say that VB it is equal to VA by using virtual ground concept. Okay. So VB it is equal to VA. Okay. Now VB it is equal to V in 2. So VA it will be equal to V in 2. Okay. So how we can express V out? Suppose this is I1 and this is current is IF. Okay. So how we can express? See, I1 it is equal to IF. Under what case? If we are considering this operational amplifier as an ideal. So under ideal case IA, that is the current flowing, this current flowing to the inverting terminal and current flowing to the non-inverting terminal, it is equal to 0. So this I1 it will be equal to IF. So how we can express I1? I1 it is equal to 0 minus VA divided by R1. It is equal to, how we can express IF? IF it is VA minus V out divided by RF. Okay. Now we have seen that VA it is equal to VB it is equal to V in 2 by using virtual ground concept. Okay. So we can write here minus V in 2 divided by R1, it is equal to V in 2. It is minus V in 2 divided by R1. So it is equal to VA is V in 2 minus V output divided by RF. You can write. So this expression it is equal to V into R1 minus V naught into R1, it is equal to minus V into RF. Okay, so this expression we can write V into R1 plus RF, it is equal to V output into R1. So V output divided by V into, it is equal to R1 plus RF divided by R1. Okay, so it is equal to V output divided by V into, it is equal to 1 plus RF by R1. Okay, so AF here, AF it is equal to 1 plus RF by R1, and we can express V output, it is equal to 1 plus RF by R1 into V into, so it is equal to AF into V into. So what is this AF? AF is the gain of this operational amplifier. Okay, so this operational amplifier is non-inverting operational amplifier in closed loop configuration. Okay, so again we can see that AF can be varied. AF can be varied by varying RF and R1. Okay, so V output, it is equal to AF multiplied with V into, which is equal to 1 plus RF by R1 into V into. So again it can be considered as a voltage controlled voltage source. Okay, suppose if RF is equal to 0 and we are neglecting R1, okay, then in that case AF it is equal to 1, because AF is equal to 1 plus RF by R1, making RF it is equal to 0. Okay, so in that case the circuit will look like this. Okay, so this circuit is a voltage follower. This is a voltage follower circuit. Okay, so V output it is equal to V into, and AF it is equal to 1 for a voltage follower circuit. Okay, so this voltage follower circuit, it can be used as a buffer, circuit. Okay, so where it can be used buffer circuit can be used in filter circuit. Okay, so suppose some portion of the circuit has to be isolated from other portion of the circuit. So we can use a buffer circuit or voltage follower circuit. For that case it is also known as isolation circuit. Okay, here V output it is always equal to V in, but it can be used as an isolator or buffer circuit. Why it is known as isolator circuit or buffer circuit? Because R in is very high, R out is very low, and AF it is equal to 1. Because of this reason it behaves as a buffer circuit or isolator circuit for some portions of the, suppose some portions of the circuit we want to isolate to other circuit. So in between these two circuits, okay, we can put isolator circuit, isolator or voltage follower circuit or buffer circuit. It behaves as an isolation circuit for two different circuits of the same system. Okay, so it can be used in filter circuit. So this is the application of voltage follower circuit. So voltage follower circuit can be made from non-inverting operational amplifier in closed loop configuration. Okay, so we have seen two types of amplifier, that is inverting and non-inverting operational amplifier in closed loop configuration. Okay, so inverting operational amplifier, it is also known as voltage shunt feedback amplifier, and it is known as non-inverting operational amplifier, it is known as voltage series feedback amplifier. Okay, now we have seen how to calculate V output in both the cases and how to calculate the closed loop gain in both the cases. Now we will see about differential operational amplifier in closed loop. Okay, so first of all we will see the circuit diagram. This is R1, this is R2, and say it is connected to V in 1 and suppose this is connected to V in 2. Okay, this is R2 and this is say R3. Okay, suppose point A and this is point B. Okay, and this is VID. So this is the circuit diagram of differential operational amplifier in closed loop configuration. Okay, now if we are considering if V in is equal to V in 1, if it is equal to 0, okay, if we are not giving V in 1, then this operational amplifier it behaves as non-inverting operational amplifier in closed loop. And if V in 2, if it is equal to 0, if this V into if it is equal to 0, then this can be considered as inverting operational amplifier in closed loop configuration. Okay, now if we are applying V in 1 and V in 2 to both the inputs, to inverting input and to non-inverting input, then this behaves as a differential operational amplifier. Okay, so in order to determine V output, we have to use superposition theorem. Okay, in superposition theorem, first of all we will be calculating V output if V in 1 is only applied and V in 2 is equal to 0. Then we will get V output when V in 2 is only applied and V in 1 is not applied. Okay, so by using superposition theorem, say if V in 2 if it is equal to 0, if V in 2 if it is equal to 0 and we are considering only V in 1, then what will be V output 1? In this case V output 1, it will be equal to how much? It will be equal to, here it is RF, it is R2 and R3, R1, RF, R2 and R3. Okay, so V output 1, it is equal to minus RF by R1 into V in 1. So we can write V in 1, it is equal to VO1 plus VO2. So it is equal to VO1, it is equal to minus RF by R1 multiplied with V in 1. Okay. Now we have to consider V in 1, it is equal to 0. If V in 1 it is equal to 0, if this voltage source is equal to 0, then only we can determine V output 2, means V output 2 is due to V in 2 only. Okay. So for this case, what will be VB? We have to determine V at point B. V at point B, it is equal to R3 divided by R2 plus R3 multiplied with V in 2. Okay. So if V in 1, if it is equal to 0, then V output, how we can get V output? It is equal to 1 plus RF by R1 into VB. VB, okay. So it is equal to, 1 plus RF by R1 multiplied with VB, it is equal to R3 divided by R2 plus R3 multiplied with V in 2. Okay. So this we can write R1 plus RF divided by R1 multiplied with R3 R2 plus R3 into V in 2. Okay. Now if R2 is if R1 is equal to R2 and RF is equal to R3, if we are considering R1 is equal to R2 and R3 is equal to RF, then in that case it is equal to, we can write this equation in upside. So it is equal to V output, it is equal to R1 plus RF divided by R1 multiplied with R3. If R3 is RF divided by R2 plus R3, R2 is R1 plus R3 is RF into V in 2. So it is equal to, this will be cancelled out. So it is equal to RF by R1 into V in 2. Okay. So V output 2. Okay. So it is equal to plus RF by R1 into V in 2. So we can write like this. It is equal to RF by R1 into V in 2 minus V in 1. Okay. Or we can write minus RF by R1 into V in 1 minus V in 2. Okay. So total V output, it is equal to VO1 plus VO2, it is equal to minus RF by R1 into V in 1 minus V in 2. We can write like this. So what is this expression? This expression is similar to that of inverting amplifier in case of closed loop configuration. Okay. So but we have assumed this. R1 is equal to R2 and RF is equal to R3, then in that case V output it is equal to minus RF by R1. Okay, so gain of this differential amplifier in closed loop it is equal to minus RF by R1. So this is similar, this gain and the gain of inverting operational amplifier both are same. Okay, if R1 is equal to R2 and RF is equal to R3, that is if here R1 is equal to R2 and if RF is equal to R3, then the gain of this operational amplifier and the gain of inverting operational amplifier in closed loop configuration both are same. Okay, so this is the expression of gain in case of differential of operational amplifier in closed loop configuration. Okay, so this differential operational amplifier can be operated in three modes. First one is single-ended mode. Second one is differential mode, and third one is common mode. Okay, common mode. Okay, in case of single-ended mode, either V in 1 is equal to 0 or V in 2 is equal to 0. Okay, so it may be considered as an inverting amplifier or non-inverting amplifier depending upon the signal that is applied to only one end of the terminal. Okay, so if we are applying to inverting end, then it will be considered as an inverting operational amplifier, and if we are applying the input signal to this to non-inverting end, then it can be considered as non-inverting operational amplifier, because here V in 1 it is equal to 0. Okay, so this is all about single-ended mode. In case of differential mode, we have to apply V in 1 and V in 2 to both the terminals, that is to inverting terminal and to non-inverting input terminal. Okay, so here in differential mode, V in 1 and V in 2, it may or may not be same. Suppose V in 1 and V in 2, magnitude may be same or magnitude may be different, but the phase here, the phase will be different. V in 1, in case of differential mode, the phase of V in 1 and phase of V in 2, it will be different, but the magnitude may be same or it may be different. So this is about differential mode. In case of common mode, what we are considering, V in 1 it is always equal to V in 2, the magnitude and phase. In case of common mode, magnitude and phase both are same. So V output, here V output, how we can get in case of common mode? V output it is equal to 0, because magnitude of V1, magnitude of V2, it is equal to both are equal. So in three cases, see, V output we can express like this: minus RF by R1 into V in 1 minus V in 2. This is the expression for differential amplifier. In single-ended, either V in 1 is 0 or V in 2 is 0. Okay, this is all about single-ended. If V in 1 is 0, then it behaves as an non-inverting operational amplifier. If V in 2 is 0, it behaves as inverting operational amplifier. Now, in case of differential mode, if V in 1, in case of differential mode, see, if V in 1, if it is equal to V in 2, in differential mode, both the magnitude may be same or may be different, but the phase it will be different. It will be opposite phase. So here we can see, suppose here it is V in 1, it is equal to minus V in 2. Okay. So in that case, what it will be? It will be like this. Here it will be minus Rf by R1. It is equal to minus 2 V in 2. So it is equal to minus Rf by R1 into minus 2 into V in 2. Okay. So it is so in this way we can determine the output voltage in case of differential mode. Okay. Now in case of common mode, this V in 1 minus V in 2, it is always equal to 0. Okay, for a common mode signal. So V output, it is equal to 0 for a common mode signal. Okay. So this is all about differential operational amplifier. So we have seen three types of operational amplifier configuration in closed loop. First one is inverting, second one is non-inverting, and third one is differential operational amplifier. And we have also seen how to determine V output in all the three cases. Okay. Thank you.